Okay, we are live now, streaming, and today is a special seminar day. I was looking here at our schedule, and we are at the end of our class. This is an official class at our Faculty of Electrical and Computer Engineering, and we are reaching the next. We are starting. June, and June is the last month, and the students will be running and doing some final class projects. But this semester was great. We had eight great seminars around internet architectures, cloud gaming, XR, quantum, AI, and 6G. We had also edge computing. We had also physical sensing, and today we have one of my preferred topics, which is networking, programmable networks, flexible, intelligent networks, so AI and programmability and networks. And I'm very glad to have with us Shaba, is professor now at the University of Michigan. We have been working together in the community of programmable networks before, seeing all these advances that the technology has brought to our domain. And I'm very excited about the talk, and even more about our follow-up chat and the opportunities after the talk to work together. Shaba, thank you for being here. And the floor is yours for up to 40 minutes, because I want at least 15 minutes for chat with you.
All right, cool. Okay, so I'm gonna share my screen.
Let me stop sharing here and then you can start. Yeah, start.
All right.
Okay.
So thank you, Christian, for inviting me, and thanks for the introduction. So yeah, so today I'm going to talk about the sort of the series of work that I have been doing in my lab over the last couple of years. Basically, the idea is like to sort of think about that as networking, we have been fast, then we became flexible, but now the question is like, are we intelligent or not? Like, so the whole sort of focus of this talk is going to be how to become like fast, flexible, and intelligent, and sort of build the next generation networks around that theme. So before I move into the details, let me just take a very high level 10,000 feet view of what is a network and what does it provide. So in my understanding, there are two main components. One is the connectivity piece of the network, and the other is more of a probabilistic security and performance aspect of the network. So if you think of connectivity, it's basically something that is deterministic. Like if you break connectivity, it will impact your functionality. So for example, if host A is sending traffic to host B, it has to be deterministic. Like it should always go, the packets should always go from host A to host B. They cannot just end up on any other system along the way. So it's a very deterministic aspect of networking, which is connectivity. And if you don't do it right, it will impact your functionality. But on the other hand, if you look at security and performance and all these other aspects, like they're mostly probabilistic. What does that mean is like it won't impact the functionality of the system. Host A and host B will still be able to talk to each other, but maybe they will not be more secure, or maybe the performance that they are seeing is not the best they could when they're communicating with each other. So given this sort of like a distinction, like we had connectivity, which is one aspect, then we have the security and performance aspects of networking. What I would argue and take a sort of statement here is like we have a very good handle on how to determine or express the connectivity aspects of the networking. Today's abstractions and sort of architectures that we have, they're very good at defining the connectivity part. But when it comes to security and performance, we have mostly relied on simple heuristics on how to determine the best path, how to enable sort of security in the sense like denial of this service attacks and so forth. So again, I would take a bold statement in this sort of talk, and I will just say that if you look at the security and performance aspect, sort of like it seems like it's a more data-driven kind of algorithms would actually benefit more in this area. So for example, machine learning is sort of, if you think of it, is the right sort of kind of mechanism that if you can apply in the heart of the network at full speed, will actually give you the best bang for the buck of handling the probabilistic or the security and performance aspect of networking. Okay, so with this distinction in place, let me just give you some examples of what I mean by security and what I mean by performance. So for security, let's take an example like anomaly detection. So think of a network with just one core switch and there are a couple of servers sitting in a rack underneath it. So if you think of this network, then let's assume a software-defined network like an environment where we also have a logically centralized control plane, which is sort of monitoring the network and sort of enforcing routing and other policies onto this existing core switch that is in there. So now when the traffic is coming in, and assume that there's certain part of the traffic that is attack traffic, what would happen? Well, in the beginning, all the traffic will let in. Like we won't be able to do anything upfront. The traffic will keep on coming along with the attack traffic. But along the way, we will start sampling some traffic from the network. And then the logically centralized control plane, if it's if it's implementing a middle box like security application, then it will sample some traffic. And then over time, it will generate some set of flow rules to identify that, okay, there is a certain part of the traffic which is an attack traffic, start dropping that traffic. And what would happen is like now after installing these rules, your traffic sort of becomes clean, and that's how you enforce sort of the state-of-the-art way of applying anomaly detection in today's network. So if you think of if you abstract this mechanism, if you think of it, it's more of like a learn and enforce mechanism. What we are doing is we are learning as the traffic is coming in, what's going on, and then after the fact, we are enforcing policies to handle the traffic in a particular way. All right. So similarly, so the thing is like if we think of the other way, like the machine learning way that I was talking about, so and assume that we have a futuristic like switch. That switch can actually do line rate ML driven sort of security enforcement. So what would happen there in this paradigm? The thing is like you already have trained a model which has a perceived view of what the right traffic and a bad traffic is from the get-go. Like it's part of the training. Now the model knows, okay, it has a certain notion of what is the right traffic and what is the attack traffic. So based on that, when the traffic starts coming in, your traffic will be clean from the very beginning. Now the thing is, yes, maybe the model has a new form of an attack has come along, and therefore the model is a little bit outdated. So during that process, it's not just that you just have one like offline trained model sitting in the switch. You're also doing the online learning element, where the model is being constantly sort of updated with new attacks that are coming in. It's being retrained and being updated in the switch along the way. But the thing is, unlike the previous design, here your switch can always start, or the network can always start with a notion of what is a good and a bad traffic, and along the way it can learn what other forms of attacks or behaviors are emerging in the network. So if you think of, again, on a high level view, this sort of like flips the way we have been doing sort of, say, policies, where we have been applying policies in the network. Instead of being learn and enforce in the previous case, now we flip it. And now what we are doing is we are enforcing while learning. So we already have a notion of what is the right traffic. And then along the way, we are learning what new patterns are emerging and updating the model in the network. Okay. So now let's flip onto the performance sort of side. Like let's take an example of a performance sort of element, which is like load balancing. Say, if you want to do load balance traffic in your network. So in this case, let's make the network a little complicated. Now, instead of a single core switch, now we have a leaf spine network with a core switch sitting over there. So let's simply take the most simple, like, or the most sort of a common form of load balancing we typically do in this network, which is like upstream load balancing. So what do we do today? So today we have heuristics like equal cost multipath that look at the pipe tuple of a packet, and then based on a hash decides which path it should take, or which upstream link it should take when going outward. Again, later on, like there is a work that came along in SIGCOMM a while back, which said, like called Conga, which said, okay, just looking at the pipe tuple alone is not good enough. That heuristic alone is very stateless. It doesn't take into account the load on the links or the load on the paths in the network, and therefore it doesn't do well in real scenarios that are out there in the data centers. So what did they do? They said, okay, let's add a new thing into that algorithm, which is path load. So instead of just looking at the pipe tuple, they now added another sort of element, which I would call feature, into the algorithm. And now the heuristic is a little bit more complicated, but now it can do like sort of load-aware load balancing when sending the traffic upstream. So if you look at this thing, what is happening here? So if you think of the 5-tuple, it's sort of like from the machine learning paradigm, 5-tuple is like a feature. Like you're taking 5 tuples, which are 5 features, and you're building an algorithm around it. Similarly, later on, you said, oh, these 5 features alone are not very good. We need another feature into our algorithm to make it better. But if you enhance it, like what about other features? For example, why just look at the path in the network? Why not look at the end servers or the virtual machines or the containers that are running on the end host? Maybe those are overloaded because of noisy neighbors or something. So you might want to bring those things as features into your algorithm to make it even more sort of efficient in deciding which path to take. But then what does it mean? That you need to have a new algorithm. And if you go through the conventional design, what you will do is any new change that you bring in means you need to go and cycle up a new ASIC. And then that ASIC will take a couple of years to come along, and then you will end up having access to it and so forth. Again, let's flip this thing. So what if you have a magical router that can do line rate machine learning in there? So it's a programmable architecture that allows you to express your algorithms as machine learning models that can take in any form of features that you can think of, and then you can program them onto this switch. So with that in mind, you can now sort of think of the previous algorithms as a form of a machine learning algorithm where you have 5 tuple as features, you add a new feature called path load. Later on, you can add more and more features and make it more and more intelligent. So with these two sort of examples, I hope it starts to make sense, like why data-driven networking can actually help a lot in here if you have such a device available to you in the network. Okay, so now I will take a small detour. I think I like this thing a lot, which is to place in ourselves as networking discipline in context with what systems people have been doing for so many years in the community. So think of in the systems, we got our first fixed function processor around in the 30s, like maybe 40s, but around in that time frame, we got our first fixed function processor. These were like large mainframe computers where the logic was baked into the device. So whenever you want to program them or add a new feature, you will have to cycle up a new machine, take multiple years, and then the machine will become available for you to use. So what happens? 40 years down the road, we got our first programmable processors in the systems community. The whole idea was that fixed function nature is too restrictive. We want to be able to add sort of new sort of changes very fast. We want high feature velocity, and we want to be general purpose so that we can support any forms of compute that we can think of. So these processors are sort of Turing complete. They can run any form of logic that you wanted to run, and that's what we got in the 70s. All right, so we went from fixed function processor to a highly flexible and programmable processor. But now, 40 years further, if you look into what we are doing today, we are now becoming domain-specific processors. The idea here is, well, the level of flexibility that we have over there is too much, and it's not when it comes to certain forms of workloads like machine learning, DSP, and graphics. Well, that CPU alone is, yes, it can run those algorithms, but it's not efficient in terms of compute, processing power, and like other capabilities that you want. So what did we do? We started building domain-specific processors. Again, they are not fixed function because they handle a certain range of a domain, and you can express any form of logic as long as your sort of algorithm or application lies within the domain. And then you have a corresponding architecture that you can compile it on and get the benefits. So for example, NVIDIA, TPU, and all these sort of the hardware architecture that we have today sort of lie in this category. And there's a lot of effort being done now to make them more and more efficient. So we went from fixed function, became programmable, and now we are becoming domain specific. Okay, what is happening in the networking now? So we got our first fixed function switch around in the 70s, 40 years after we got our first fixed function processor in the systems community. And again, it makes sense. We need to have systems, or we have to have something to connect before the switches can come along. So with this, again, 70 years down the road, we got our first programmable switches. So these are the switches like P4, Tofino, like these Broadcom switches. So they are now not fixed function. You don't have to go and talk to the vendor to add a new header or a new protocol. You can just express your networking logic onto these programmable devices using a high-level language like P4. Again, if you see the comparison, we are sort of running 40 years behind systems. Just like I mentioned, we need to have systems first before we can start connecting, start thinking about networking. But now let's see what's next, like, because this is where we are in networking at the moment. So if you think of it in terms of timeline, networking is now at a point where we were in the 70s with the systems, right? So this is how I place it. Again, some people may argue that this is not the comparison, but I think this is how I place it, where we are now at a point where the systems community was in the 70s when they started getting their first programmable processes. So what is happening next? So what is next for networking? So I would argue, just like we have domain-specific processes now to sort of handle a certain class of applications like ML, if we want to add ML-like support into into the network today, the existing architecture is not sort of, I would say, efficient enough or designed for that sort of domain. So we need, again, that's my sort of thesis, like we need a domain-specific switch now that can sort of enable the things and examples that I just showed you in the last couple of slides. So let's look at this thing in a different way. So think of it like we had a CPU, a new workload came along called machine learning. What did we do? We did what a naive thing, we like whatever we could do as a first step, right? Like we took the model, we took the workload, and then we compiled it onto a CPU, and we tested, okay, whether it works or not. It's the same exact thing that we have been doing in networking. We are taking the model or the new workload that is coming up, and we are trying to sort of run it using the programmable abstractions that we have, like match action tables onto these switches. But I hope all of us agree now that this is not the right way. Like just like running machine learning models on CPU is not efficient. Similarly, doing the same thing on a programmable switch is not an efficient design. What did we do in the systems community? We started building domain-specific architectures. We came up with an abstraction that is more closer to that domain of workloads that we want to run. So what is happening in networking? We are not there yet. Like this is the sort of place where I would say the rest of the talk will focus on, which is we need a similar thing as to what systems has done on the domain-specific side. We need a domain-specific switch, but we don't know what that architecture looks like. We don't have a notion of what the abstraction should look like. Should it be a match action table, or should it be something more? And how to then run these workloads efficiently onto these architectures. So rest of my talk will focus on these two things. Like in the talk, I will show that one example of an architecture that actually can work here. Similarly, some examples of how you can take these workloads and compile them down to those architectures. So coming back again, what is the goal of this talk? So the whole idea is like we want to bridge the gap between speed and intelligence. Basically, in a more precise form, we want to start by doing inference inside switches and NICs at very high speed. What can it enable? It can enable us to learn and adapt to the network-wide behaviors quickly, apply actions directly onto the packet rather than relegating them to a control plane and then taking the outcome and applying that outcome onto the packets, which is a slow process. And what it can sort of deliver is like it can allow you to enforce fast response time, high performance, and enabling sort of stringent security level objectives for your network. Okay, so let's start with the first thing, which is the architecture. So in this set of slides, I will talk about Taurus. It's a data plane ML switch. Basically, it introduced a new sort of hardware abstraction for running machine learning inference in the data plane. So basically, the idea here is like we want to take a data plane and we want to do ML inference inside that data plane. So how can we go about doing it? So let's just look at what does a simple ML inference looks like. So let's start with neural networks. That's what we took as a representative example for sort of thinking about, okay, what if we want to run this in a data plane, what do we need? So if you think of a neural network, what is it? It has an input layer and output layer with a couple of hidden layers sitting in the middle with neurons in each layer. And if you zoom into a neuron, what does a neuron looks like? A neuron is basically a set of input features coming in. You do a dot product with a set of weights and biases, and then you pass it along through an activation function. That is what a simple neuron is. And then you aggregate a bunch of these neurons together to build up the final neural network that you want to run. Okay, so now let's go and look at what do we have as a state of the art today in the data plane switches. So today we have this thing called protocol independent switch architecture, PISA. this is the architecture that is sort of today exists in all the data planes that you think of, Tofino, Broadcom, Trident, and so forth. And there, what is happening? So what do we have is we have a packet parser that takes a stream of bits, converts them into a set of vectors. These vectors then follow through a set of match action tables, and then finally being passed through a traffic manager to enforce the sort of ordering policies and buffering and so forth. The main compute element in this switch is basically the match action tables, which is a lookup followed by a VLIW instruction. But if you look at it, it's not suitable for inference operations. It doesn't hold the necessary arithmetic intensity, which is too low to perform ML operations, doesn't have intermediate storages, and many other features that are needed to efficiently implement a machine learning algorithm onto these match action tables. Yes, just to highlight, like if you have an infinite many match action tables and you allow recirculation among them, then it sort of becomes a Turing complete architecture, but then again, it's a highly inefficient architecture. To run a very small model, you would end up taking tens of match action tables on a switch, which again is inefficient, because if you have a right architecture, you can even run much larger algorithms using a much smaller chip area if you have the right abstraction to implement that logic. All right, so what should we do here? Like, so first of all, look at this switch. Again, we think of this switch as a singular processor, but it's already a heterogeneous architecture. We have a packet parser, which is a totally different architecture with a finite state machine. We have a sequence of match action tables, which is a totally different architecture in terms of what it does. Similarly, we have a traffic manager, which also has a totally different architecture. So we already have a heterogeneous set of computes sitting inside the data plane. So if we want to like handle machine learning workloads, what should we do about it? So remember how match action tables came about. They came about because we looked at the networking workload and we found that across the board, layer 2 switching, routing, access control, they had a certain sort of a set of building blocks, which was basically to match on a certain header and then do an action. So we took the abstraction from those set of workloads and then build a corresponding architecture for it. So maybe we can apply the same strategy here. Like, for example, if you go and look at the neural networks, what are they? Like, if you look in the form of an abstraction, is there any abstraction hidden between these sort of operations that we are looking at right now inside a neuron? So if you look deeply, you will see that there are two main sort of forms of operations that are happening. One is map. That is, you take a set of input features and you map them onto the weights and you get the corresponding value. So that is sort of like a map operation that you're doing. Similarly, there's a reduce operation that is happening afterwards to pass it through the activation function. So what we did in this work was we took this as our high-level abstraction. We said, okay, just like match action table, now we have a map reduce abstraction. And if we have map reduce abstraction, so if you take that abstraction, you can actually implement any form of a neural network or any form of a machine learning data-driven algorithm by like sort of stacking them together in the form of a neural network or in the form of a decision tree and so forth. And then if you have the right architecture to run these map reduce sort of collection of map reduce operations, then you sort of get the performance that you're talking about. So the challenge here was first identify the abstraction, which we said map reduce. Now the goal is, okay, can you build the corresponding architecture for it that can run inside the switch at line speed to sort of to be able to sort of provide the necessary throughput and latency requirements that we have in the modern network. Okay, so let's go back to the original architecture of the switch. So what did we do? Again, I mentioned it's already a collection of heterogeneous architectures. What we did was we added a new block in there, which is a map reduce block. So this sort of a block sits in the middle of the pipeline. There's a reason why we did that. I'll explain that in a bit. And then given this block, now you can actually run those sort of hierarchical map reduce blocks that you thought, like that you converted your neural network into onto these switches. Okay, so let's look at what the map reduce block is. So what is happening in here is like you're passing some features into the block. And how are these features coming in? These are basically the same, what you can say, header vectors that the packet parser has converted the bits into. And then you pass them along the match action tables to sort of do some sort of pre-processing, like want to add new extra features, like for example, for a given IP, let me know how many failed logins were there. So you can do a bunch of pre-processing using the match action tables, stack up your features, and then pass them along to the map reduce block. After the MapReduce block, you get a decision. That decision is then something that you can use in the post-processing match action tables that are sitting in here to decide something. So for example, if it's an anomaly detection application, what you can do is, if the decision is, say, if it's a binary network, it's 0 and 1. So if it's 1, let the packet go. If it's 0, either drop the packet or route it to some sort of third-party middle box to sort of do further post-processing on that packet. So these features and decisions are being carried in the switch pipeline using packet header vectors, which is already there in today's sort of programmable architectures. So okay, so now let's zoom into what is this top MapReduce block actually is. So if you zoom in, it's actually a sort of a checkerboard style architecture of control units and memory units. And we took inspiration from the work that is being done in the architecture community on building AI hardware. So there too, they are focusing on sort of this sort of grid-like architecture of compute and memory elements. And the challenge there is how to place these. What should be the density of compute versus memory in those architectures to be able to do certain workloads better than the other. So we went with the simple design. We just said, okay, we will have this checkerboard style architecture where we have a set of control units with a memory unit. And now what happens is, if you look at that neuron that you had over there, you can now actually, that one neuron then maps onto this sort of a pair of control unit or memory unit as a basic unit. But if the neuron is bigger, then it can span to multiple control units and memory units. Similarly, all the other neurons that you have, they actually end up getting mapped onto this grid of control units and memory units that we have here. So the MapReduce block, the control unit is basically, further if you zoom into it, is actually an array-based style architecture with functional units and pipeline registers. So these lanes that you see here, lane 0 to 3, they form the map part. Basically, this is how the operations are being done in parallel. So this adds parallelism. And then in order to do the reduction part, we have these reduction networks where the outcome of the previous stage gets reduced onto the next one. So this is how you implement your map and reduce architecture or the abstraction onto this hardware that we are showing. All right, so coming back to this, the new architecture, like the torus that we talked about. So we have a new hardware architecture sitting in the switch. So the next question that comes up is, how do you program this? So if you look at P4, and again, I would say we call P4 as a singular language, but it's actually a language of different sort of abstractions sitting in it. Parser is implementing finite state machines. Ingress and egress mats are implementing match action tables. And then we have a deparser to put everything together. But in the middle, we added a new control block, which is what we call a spatial control block. So spatial is actually another open source language that allows you to express these MapReduce like blocks and stitch them together. And then you can take that representation passed through a compiler and then put it onto the architecture that we have on the switch. If you look at the MapReduce abstraction further, it's not just designed to handle machine learning models like CNN, DNN, and SVM. MapReduce by itself is a very strong abstraction. You can think of it as an instruction set, a low-level instruction set that can do a lot more. Just like, for example, we didn't know when the designers of the map action table, like the P4 switches, didn't know what other applications will end up running on the switch. So we now see that we run packsaws, we do a sort of decision trees, and we do other forms of key value stores onto match action tables. Similarly, MapReduce, again, it's a low-level abstraction that it can allow other things. So we did some follow-up work. We did some sort of work for receive side scaling, gradient aggregation, and countment sketches, and we found that they actually map more natively onto MapReduce compared to mapping them onto a match action table. All right, so let's move on to evaluation. So we did two forms of evaluation. One was to sort of do an ASIC study to see whether having such an architecture in a switch, is it feasible? How much area does it take? And how much latency will it add in an actual ASIC? And then we also did a end-to-end sort of evaluation using an FPGA-based prototype. So let me just first talk about the ASIC evaluation. So in this one, we had we took two models, SVM and DNNs, and then we and these models were actually taken from the past papers, what people were proposing in terms of the models that they are writing for networking. So we took those models, we brought them in here, and then we sort of synthesized an ASIC that can actually run these models. So it's large enough to run these models and support these models. So with that, we found that SVM and the DNN, they were both able to sort of meet the line rate, a billion packet per second. The latency they were adding was in the orders of hundreds, like 83 nanosecond for SVM, 200 nanoseconds for DNN, and area and power utilization was not that much. Now you can ask the question that already in the data plane switches, the port-to-port latency is around, I think, 800 to a microsecond, or maybe 500 nanoseconds. So you're adding a lot of latency on top of it by introducing a new hardware block. So I would argue in that sense is like the comparison is like if you're comparing from a switch perspective, like something which is old, where the rules are already installed, and you're saying, okay, this is the end-to-end latency of that switch, and now you're increasing it by 200 nanoseconds. That is not the right use case. The use case is we are now able to do the processing that was previously happening in the control plane. And the time that the control plane path was adding into your end-to-end sort of performance was in milliseconds or tens of milliseconds. We have brought that down into a couple of nanoseconds. So that is the right comparison, like from the end-to-end perspective. And this is where you get the benefit by having doing something in the architecture or in the data plane or the network itself. Moving on, we built a converged test bed that I mentioned. We have a FPGA-based prototype, and we built it in a way that we could do both the baseline evaluations as well as the torus evaluations on this architecture. So we had a server and a Tofino switch, and the Tofino switch was connected with the FPGA in a bump in the wire kind of a fashion. So if you look at the baseline, the way we implemented the baseline was that we sample traffic using XTP. We store it in a streaming database. Then we apply inference onto these packets, and then we store the rules in the switch through ONOS on the Tofino switch. So this is basically how the sort of the sampling-based architecture was running. Traffic is coming in, the control plane is sampling it, it's running machine learning inference on top of it, and the outcome of that inference is now being stored in the switch and then being applied onto the packets that are coming in. Compared to that, for the FPGA, for the torus design, what we had was a bump in the wire processing where the traffic is coming in. The first pass through the switch was considered as the post-processing pass. Then it goes through the FPGA block running our torus architecture, like the MapReduce architecture, and then it goes back into the switch and then goes out as the post-processing pass. So ideally, if it was an ASIC, this block should be sitting inside the ASIC. But again, we are building a prototype using FPGA. So this is how we ended up building it. And you can think of it as a 100 gig switch that has the capability of doing MapReduce in the data plane. And the packets are basically going like this. Okay, so in terms of evaluation, we did sort of two forms of evaluation. One was basically the events that are coming in and the sampling rate. So I just want to point out that this blue line torus is actually independent of the sampling rate. The sampling rate is there because the control plane needs to have it. You cannot send the entire traffic into the control plane. You need to sample it. So as you increase the sampling rate, how the control plane was basically performing is what you are seeing here. So you can see the torus architecture is basically independent of event rates. We are changing the sampling rate, but even like with the best sampling rate possible, the gap between sort of like the control plane and the data plane was around 22 times. So it was actually, torus was actually handling 22 times more anomalous events compared to the software-based control plane design that we had. And in terms of like the F1 score, because the whole model is running in the data plane, we were running at full accuracy that we got. So the model accuracy, the offline model accuracy was 71.1, and this is what torus was able to maintain. But depending upon the sampling rate, software was actually, so the F1 score for the software was varying. And the reason for that was, if you are slow in sampling and finding out what's going on and installing a rule, majority of the traffic has already gone by. And the F1 score was being computed on what the receiving traffic was holding, right? So if majority of the traffic have never been were not seen by the new rules that you installed, you will get lower score. And this is what you're seeing here. The faster the response was, the higher the F1 score was, the lower the response was, or the lower the sampling rate was, the lower the F1 score was for the software-based baseline. All right, so with this, let's come back to the same picture that I showed you. Like, we know that in the systems community, we have a stack, we have an architecture, we have an abstraction, and then the workload actually gets compiled onto that abstraction. So what do we have now after this exercise that we did with torus? Again, we have a architecture. Again, I won't say that Taurus is the architecture. I'm just saying it's a first step in that direction of coming up with an architecture that allows you to do machine learning workloads onto the data plane. We have come up with an abstraction, which we call the map reduce abstraction. And this is how the ML models then compile onto these this underlying architecture. Again, I know I have 40 minutes, so I'll go with the next slide a little bit faster. But the other point that I want to make here is the question that I would like to pose is, are we done? Like by doing this exercise with Taurus, are we done in terms of the stack that we need for running ML in our networks? Again, I would argue no, because if you think of the systems community, nobody write code. Like as a domain expert, like the machine learning developers, they don't write code in CUDA or low level sort of like languages or instruction sets that they have for TPU. They work in a high level abstraction like PyTorch or TensorFlow. And then that gets compiled down onto the underlying architecture through the sequence of compilation steps. So the question is, what would that higher level abstraction? So from the customer standpoint or the network operator standpoint, what would that high level abstraction look like? Is PyTorch good enough? Again, the argument is PyTorch works because the domain expert is an ML developer. He knows what an ML model looks like or what the ML model like sort of does. So they are the domain expert in machine learning. But on the networking side, the domain expert is a network operator. They don't necessarily know the details of how a machine learning model works, or maybe which one is the right model. Should we pick k-means, neural networks, LSTMs, and whatnot? So the abstraction for the networking side is even higher level. So this is where we again did the next work, which we called like again I'll show you. But again, let me just show you why it is hard to sort of express the crafting your ML pipelines. Basically, as a network operator, what would they have to do? They have to sort of do model selection, architecture search, parameter tuning, backend compilation, constraint checking, and then this circle goes on and on unless they get the right binary, which then fits onto the underlying architecture. So again, clearly, this is not the sort of the high level abstraction that the domain expert is looking for in networking. So what we did was we actually did another work called Homunculus. It's sort of like a declarative compiler, which allows a much higher level abstraction to the network operator than what is already given by PyTorch or TensorFlow. So we call this a Homunculus. It has different layers: Alchemy front-end, optimization core, and the backend. So let me just quickly go through it. So in terms of the operator, like what do they do? So the abstraction that is given to the operator is basically very high level. They just have to give us a data set because they have access to it. They need to tell us the objective, like what speed, what performance, and things that they're looking for, and what target they want to compile to. Do they want to compile to an ASIC? Do they want to compile to CPU? Do they want to compile to the FPGA? That's the target that they have to specify. And then they go through the sequence of steps. We have the declarative language. We compile it down. Again, I'm going to go a little faster. We compile it down. It goes through the optimization core. And now the optimization core is taking on the responsibility of finding or doing a domain search for finding the right sort of model for you. So as a network operator, you told us your objectives, data sets, and target. Now the compiler will do the domains, like sort of the design search. So it will build up a design space, and then we use Bayesian optimization to explore that space. And then we do training and testing to pick which one is the right model for you. So as an operator, I didn't show here. So you can define what models you want to explore. Do you want to explore DNNs? Do you want to explore k-means? Or if you don't specify anything, then we will explore all the possible set of models that we have in our libraries. So with this, we do the training, then we pass it along to the backend engine, which does the feasibility testing. Then the sort of the results are sent back to the optimization core, and then you get the final binary. So this is like an iterative compiler, just like Xilinx or Cadence do. So we do this iteratively to find out what is the right sort of model and the binary for that one. So again, why Bayesian optimization? The idea is like this whole sort of compiler framework is very complicated. So you need sort of kind of an algorithm that can give. So first of all, it treats the whole thing as a black box. And then based on inputs and outputs, it is sort of progressively giving you better and better outcomes. So you came with a model, you ran it, it didn't fit well. The input goes back to the optimization core. Now the optimization core should be able to prune those things out and be able to give us other better solutions that we would like to explore. So this is where we used an open source tool called Hypermapper, which is a Bayesian sort of optimization sort of parameterized it does the parameter space search using Bayesian optimization, and is an open source tool that is being used by many out there. So we use the same tool in our solution. Again, we go through the optimization loop again and again, And then finally, we generate the final binary. Okay, so let me just close, quickly go from the evaluation. So again, we took the baseline example from a paper. We saw how many features they had, what number of neural network parameters they had, and what F1 score they were getting. And then we did the same thing by giving the high-level data set, objectives, and target. And we found that Homunculus was actually able to find better F1 scores and better models. And you may see that, okay, our Homunculus architecture is picking up more parameters, so it's a bigger model than the old one. But you can see in some cases, it was able to get even a better model, even using less parameters than the handwritten one that we got from the paper, the sort of the previous paper. Okay, coming back here, I would say that now we have done one other step in that direction of building a high-level declarative abstraction for the domain expert network operator to compile our sort of his intent or her intent onto the architecture. And now we have done some other work, but let me just go into like the other set of challenges that exist in here. So again, just like I mentioned, Taurus is one step in the direction of building architectures for ML for data planes. There's a lot of more work to be done, scaling to larger models, handling sparsity, model training, newer abstractions, and also doing floating point operations. These are all open areas of research we haven't explored yet. Similarly, on the sort of the abstraction side or the compiler side, feature engineering, data collection, auto labeling, model design, all these are open areas that we need to explore to sort of make it this sort of whole idea of in-network ML a reality. So basically, what I would say is the theme is for us to make any tangible progress in that direction, we need to combine forces from ML, network, and architecture to be able to co-design these new and emerging architectures for these new and emerging sort of workloads and sort of problems that are emerging. All right, so I think I'm a couple of minutes over. Let me just finish with this last slide. So I really like this sort of portion because I think it's a very nice sort of insight that is happening. So if you look at the system side, we were highly flexible. We were CPUs, and now what is happening is we are becoming domain specific. Why is that? We just found, right? CPUs are highly flexible, but they are not very good in performance when it comes to these emerging workloads. So we are becoming domain specific. What we are doing in that case is like we want to gain higher performance. That's why the green part. But we want to do so without losing flexibility. So that's why the notion of domain specific architecture is coming up. Okay, so what is networking doing? So if you look at networking, we are actually also doing the same thing. We are also becoming domain specific. But our objectives are opposite. We were fixed function. Performance was never an issue for us. We were always line rate. It's the flexibility that was a concern for us. So unlike systems, networking is becoming domain specific to gain more flexibility. But the objective then is to minimize the loss in performance. We want to become more flexible, but we don't want to give away performance in doing so. So in that regard, we have done some work in my lab on the system side, similarly on the network side. And then the goal is basically to realize the full potential of this fast, flexible, and intelligent next generation systems and networks. And with that, I'm just going to close off. So thank you, everyone. I hope you liked it.
Thank you, Shava. Lots of contents,
Yeah.
man, and thank you for keeping to the time so that we can chat a little bit.
Yeah.
Let me ask you to stop sharing, and I want to show you, and not only you, but the rest of the students, and maybe those who may be seeing this offline. Just to explain that in this class the students do their homework, and that is what I was telling you, that we have over 40, and you can barely see, but they had to come up with 5 topmost related works. Of course, your publications are there. And I hope that they argued that not just because ChatGPT recommended it, but because it's in the abstract. And then they have this other that they elaborate at least one question. Okay,
Yeah.
I have selected a couple of them, those in green, just 3
Yeah.
or 4. I myself would have tons of questions to talk to you that we don't know the answers, right? Many
Yeah.
of the questions we don't know the answers, but I just want to recognize the efforts of our students and bring at least some of them. And those that were not selected, please keep in mind that there is limited time.
Yeah.
And this one was well elaborated. Okay, let me summarize it for you. It goes into a little bit uh, my interpretation of this is okay. Now you have published this great work. You have shown, you have this idea of the model of a next switch. I love your analogy that you borrowed from of course from our community what would be next. What is next? So how do you see something like this architecture, like Taurus could become a influence a vendor to extend or the P4, and now you can plug in, of course, your P4 educational role. What is next into bringing these ideas from publications into something more tangible that we may
Yeah.
see a few years later in production?
Yeah. So I think so this is a good, like a very great question. This question actually sort of like sits like it's sort of addressing not just what we are doing, but what we have already done in the community with P4 data planes and programmability and all that. The question is, okay, why do you need that programmability? The whole notion was that, hey, right now making a change takes 2 years. We want to do it faster. But the question is, okay, how fast? What is the feature velocity you are looking for, right? Like, who's the customer? Like, if the feature is going to come in and it's going to stay there for 3 years, then maybe the speed of what we have today with the ASIC is fine. I think if you are trying to sort of challenge that aspect, then I think the whole notion of programmability is to find places where there is a need for change and there's a need for frequent change, right? Otherwise, if it's a one-time change, then you can always build an ASIC which will be much more efficient, power sort of like in terms of power and compute. Uh, but I think in terms of this work, again, our hope is that there is enough diversity and need out there in terms of the probabilistic part of the network. So the probabilistic part of the network has a higher feature velocity in terms of if you look at the kind of load balancing, traffic engineering, and all these algorithms that are coming out, congestion control, packet dispatching. So unlike the connectivity part, which is to decide, okay, where you want to go, which is a little bit more rigid than the probabilistic part, that is our hope. Like, okay, there is enough feature velocity here that given this architecture, they would end up getting the benefit. And also, there are two ways to look at it. One is like networking for ML, and the other is ML for networking, right? So we have done this. The work that I've showed you mostly is in the form of ML for networking, but these architectures are also ML where you can do in-network like gradient aggregation and things like that. So it all comes down to the feature velocity, how fast you want to change. But I just want to point out, again, I'm giving it a shout out to Broadcom. They already have a feature in their new Trident X15 where they have a fixed neural network. So the number of layers and neurons are fixed, but you can program the weights, right?
Oh,
It's
I,
already there in their chip and you can try it. Like, it's a small model, but the thing is, like, there it's still rigid, but it's still flexible in a way that, unlike expressing the entire neural network, you can only modify the weights of that network. And you can try all these sort of examples in there if you want to.
I didn't know that
Yeah,
about our friends at Broadcom. It's not unexpected that we
yeah,
would see TPUs or other AI accelerators down
yeah.
there to the switch. That's that's great news.
But then
Uh,
again, that is actually sitting, it's like tightly integrated in the pipeline. It's not like a separate chip like a TPU. It's on the same ASIC in the middle of the pipeline. Yeah.
Another stage that you can move
Yeah.
the packets. That's interesting. And I would argue that the other part that it really resonates to me, the higher level ML, the feature selection, the automation of all
Yeah.
this could have its own life,
Yeah.
independent, and also be much faster or amenable for adoption because it's just software
Yeah. Yeah.
only.
Yeah.
It lives in the software domain,
Yeah.
right?
Yeah.
But the co-design term, it's really a one for those working on
Yeah.
software hardware aspects.
Yeah.
This other one, it's a classic one, but I need to recognize it.
Yeah.
How do you do retraining? So now
Yes.
you have the model, and now you how do you adapt?
So the thing, like, this is the work that I briefly mentioned, like Caravan that we did, like in OSTI last year. So that was all about online learning. Like these models that we have are very small. So if you do a one-time like sort of training and then expect that model to work for the entire duration of the network for the entire life, it doesn't work. New changes, new behaviors are coming all the time. So let me first handle the engineering part. So the thing, you start by first defining the parameter, like model itself, how many layers, neurons, whatever the structure is, that's an offline element. Then using that, you train it, and then you install it into your data plane. Now, after that, how do you update it? So if you want to change the structure of the model itself, like new layers and stuff, then it has to be an offline process. You need to turn it off and do it. But most of the time, when you talk about online learning, you're not changing the structure, you're only changing the weights of the model. And that is actually just like installing new rules in the flow table. And it's actually much faster than installing flow rules because you're just writing 32-bit values or 8-byte values compared to updating a TCAM. So if
Yes.
we can update the TCAM at line rate, we can also update these weights at line rate.
Very, very good. Well, this is a great answer. I will reuse it because I get it all the
Yeah,
time.
yeah,
That's excellent. You see why I love these seminars,
yeah,
because it's time to catch up as we were doing before the start, and I repeat, Shaba, you didn't have access to these questions.
yeah,
And I myself, I open them also at the time that the seminar starts.
yeah,
This puts
yeah.
me also some good energies into it. So, last one that I wanted to, let me see when the return. So that was already taken. One more. I don't see any from the chats. Yeah, I recognize this was a very
Yeah, yeah,
deep down for our class. Okay, I know the broader audience, like our friends in the P4, Tofino, and other communities will love. Uh, okay, this is another classical one that for sure you also get.
yeah.
Security, privacy. Do you store IPs? What are the potential issues around
So,
privacy?
so, so this is a classical again, very good question. The thing is, like, first of all, there are two ways to look at. So there are two forms of questions we get here. One is like, okay, what if the model hallucinates and starts behaving badly? Like, how do you ensure that you're not doing bad behavior because of the model saying you something? So this is where we again bring up this notion of like pre-processing and post-processing. We always can apply the symbolic sort of model, like the things on front of it. Like, okay, the model is telling you that, but if it's deviating beyond a certain threshold in terms of what it's suggesting, then you can sort of fall back to the traditional sort of flow rule based decision making for those pieces. Again, the hope is that those kind of sort of instances are much less. Only then it makes sense to have the model in the middle. But if the model is behaving bad all the time, that means there is something wrong with that person. You need to train it and make it better. So the other part is like in terms of what we want to like as features to pass through the model to do some decision making. That's a very good point. So the thing is, the sort of the question that we have been getting from folks is like, if you are talking about just headers, packet headers as your features, then the kind of knowledge you can sort of gain from those features can actually be done very nicely with the heuristics itself. Like, you don't need a very complicated model to sort of look at those header features and do something. Again, I have my own beef with that. Everybody has their own opinion. But yes, I agree in some sense that the header alone does not carry that much information that might be useful for you for, say, application layer, sort of capturing application layer behavior or payload level behavior, right? So the question is, okay, as long as we are on the packet level, security is not a concern because we are looking at exactly the same information what existing switches were already looking at. Now the question comes up is like, if you want to do something like where Snort, for example, or Suricata, like these are the sort of software tools that do deep packet inspection to find things within the packet and then use them as features in your model to do something. Well, there are challenges. Like, this is again the next set of work we are doing, where do we need to know exactly on a bit level what a payload carries? Like, for example, do we need to know it's a HTTPS header, or do we need to know it's a gRPC header to use it as a feature? Or we can actually sort of approximate it by looking at the payload. So, for example, n-grams, frequency distribution of the bytes, and so forth, so that we don't necessarily have to look at the exact value, but looking at the bit stream distribution from packet to packet, we can capture, the model can actually capture something on top of that. Like, oh, I'm seeing this forms of bits for this payload versus this one. So maybe this one is bad versus the other one. Again, it's an open area of research. We are exploring. I'm sure other people are exploring. So we'll see what happens in that space.
Yeah, yeah. Many colleagues are working on the federated learning
Yes.
type, right?
Yeah.
And if the models are small, even they could flow
Yeah.
in packet, right, or on path, and the
Yeah.
switches would be the inline sort of.
So I think one thing I forgot to mention in that sort of question was, how do you keep the model up to date? So this is again a Caravan paper that we had, where we have this thing called accuracy proxy. So we are tracking what the model is doing, and the moment it starts deviating from a certain accuracy levels, then the what we call there, what we have introduced as a notion called knowledge sources. So these knowledge sources are running in the control plane. These are like large language models, big DNN models. So they're also sampling traffic. And the moment they see that, okay, the small model is not behaving because new patterns have emerged, there's an online learning piece that comes up. So the moment we see, okay, the model is deviating, we do an online learning pass, we update the model, and then we keep on going. But the thing is that pass is happening on a second level. So we have time to do it in the software. We don't have to do it on a nanosecond time scale. So we have an opportunity to use the control plane.
Good, yeah. And now another on now from my own from our
Yeah.
research, and I know you work on smart mix.
Yes.
Most of the things that you have presented are on the switch perspectives. How do you see this? Do you see an heterogeneous, like we will have the smart mix and the switches, and together distribute and find the better trade-offs,
Yeah.
or maybe some of the switching techniques that you presented will move all over to the smart mix and then will overlay the network. I know this is
So
the very
yeah,
tricky,
so I
but
think it's a
what
very good question. It's a very good question. So basically, there's already some work on the next space. So think of it like the Taurus architecture that we presented is for a data plane. So wherever there is a data plane, you can run it. Like a smart NIC is a data plane, a switch is a data plane. So you can run it on a smart NIC. And there is already examples. Again, I'm gonna shout out to Marvell. So they are doing some work on their NIC to add support for inference. There is things from NVIDIA called converged accelerators, where there is a NVIDIA sort of small GPU sitting in front of the ConnectX chip. So it's basically a data plane with ML support already in there, not on the same ASIC, but in a sort of a chiplet design or of like sort of a multi-chip design. So people are already doing this thing like on these places. So that is one way. Taurus can run, just like match action tables are there both in NIC and the switches. The map reduce block can be both on the NIC and the switch. So that is one thing. But the other thing is switches, the main piece in this whole data-driven architecture is like the access to features, right? So NICs are actually in a very good spot where they are very close to the application layer. So they can actually look at features on the application layer, encode them in a header, and then send them off to a network where they can then look at those features. So they can participate a lot, even if they are not doing inference themselves. Yeah.
and that resonates a lot with the inverse telemetry ideas that
Yeah.
one of my PhD students has, Francisco. And now we have questions from Fabio also on LLMs fitting transformers into programmable data planes. But the bad news is that it's 2 p.m. Brazil time.
Yeah.
What time is it over there, Shaba?
1 p.m. our time.
Yeah, we are just 1 hour. And
Yeah.
here our students have other classes
Yeah. Yeah.
starting, and we need to be strict to time, deterministic as the Tofino Harbor pipelines that they promise a certain delay, processing delay. And with that, and thank you so much
All right.
for your time, and congrats for your work. And let's catch up.
Yeah.
Let's looking forward for working together. And regarding our class and seminars, we'll be stopping now the YouTube seminars for actually until August, and the students will do their final class projects. But we'll be back. Okay, we'll be back in the second semester. And thank you all for your attendance. Keep safe.
Yeah. All right. Thank you. Thank you, everyone. Thanks for having me. Take care.
Thank
Bye.
you.